Okay, this is the very short lecture on 3.2. I didn't want to rush the actual lecture today for 3.1 to fit this in, but it also is not long enough to warrant a full lecture period. So that's why we're talking about it here in a separate video that you can just watch. Make sure you have it. The main thing is going to be the theorem that's written up here on the board. I'll go over a quick example and then a few of the more important properties that are going to be significant results. Aside from that, the main thing is definitely have a strong base in 3.1 and you'll be pretty much fine for the rest of chapter 3. So the theorem here is if I have let A be a square matrix, as we found with 3.1, we need n by n matrices if we're going to compute a determinant. And the first thing is if a multiple of one row of my matrix is added to another row to produce a matrix B, so if I perform that row operation of row replacement and then call the next basically row equivalent matrix B, then the determinant of this B is just the same thing as the determinant of A. I alluded to this at the end, near the end of the previous lecture for 3.1. Doing row replacement to a matrix doesn't actually change what the determinant computation ends up being at the end. And that's going to be useful because when you want to get to echelon form for the diagonal entries, then we can kind of just, for the most part, know that it's going to remain unaffected. Now there is one thing, that the second part here, if two rows of A are interchanged, okay? So this is where you're actually, say, swapping the locations of row 1 with like row 4, for example. If you were actually swapping the rows' locations, then what we're going to do to the determinant of the swapped matrix is it's the negative determinant of the previous. In other words, swapping, another way to think of that simply is every time you are doing like row reduction, and you swap out two rows. So this isn't row replacement where you're scaling, like row replacement's where I'm scaling up a row and then adding it to or subtracting it to another row. That's row replacement. That's different than row interchange. Interchange is swapping their spots. And every time you do a swap, you need to multiply the resulting determinant by negative to counteract that swap. And then the last thing is if you take a row of A and you scale it up by K to produce another matrix, then the resulting matrix determinant is essentially the same thing, but now we just scale up the determinant appropriately by K as well. So these three rules, they're in the textbook. Write them, memorize them, know them for computation, because combining those tips with the general cofactor expansions from 3.1 is going to make computing pretty much any determinant really easy. So let's do this example. Compute the determinant of A, where A is, we have a 3 by 3. And so what we're going to do is instead of just doing like a brute force cofactor expansion across the bottom row or whatever, let's actually do some row reduction. Because if I can get this into, if I use row reduction to simplify this matrix, there's going to be easier ways to get to the answer, faster ways to get to the answer with less painful computation. Now, with this specific example, we'll find that there are really two good ways to go about this, so I'll cover both. And both are perfectly fine, both are acceptable. Again, there's not really a right or a wrong way to go about these. So long as you follow the rules, don't break the rules, and do it as efficiently as possible, it's fine. Okay, so the determinant of A is, I'm going to use now my determinant notation for 1 minus 2, 1, minus 4, 8, 7, 2 minus 9, 0. Okay, so what this theorem tells me is if I do, like, so this first part, if I perform row replacements, then I actually don't change the value of the determinant at all. So what I can do is the determinant is going to be the same so long as all I do is a row replacement. So the kind of row replacement I'm going to do in between these steps to this is I'm going to zero out this minus 2, zero out this 1. So in order to zero out this one, I'll first reproduce the top row. And by this time we get to this stage of the class, I am assuming that you can perform these operations pretty smoothly and consistently. Notice that if I have minus 2 here, I can add it to double the first row. So I take R2 and I'm going to add it to double the first row. And that'll produce 0 by design because of minus 2 plus 2. 8 plus negative 8 is 0. Negative 9 plus 4 is, so 5 minus 9 is minus 4. Okay, so for this one, for the third row, I'm just going to take, 1 and 1. So I'll take row 3 and I'll subtract row 1, and that's going to be how I row replace. So 1 minus 1 is 0 by design. 7 minus negative 4 is a positive 11. And 0 minus 2 is negative 2. Okay. Now, from here, what I can do is I'm trying to get this into echelon form. Or I could just take advantage of my string of zeros. So when I get to something like this, this is where you can use whatever tool is going to be the fastest for you. The way I'm going to show you first is kind of going to be similar to what we talked about in 3.1. Now that I've done my row replacements to get this, I know that these determinants are equivalent because of this theorem right here. Now this is much easier to do a cofactor expansion. What if I just do a cofactor expansion right down this first column because of the 1, then 0, 0. So I have effectively 1 times the determinant of, and then so if I cover up the first row, cover up the first column, I have 0, 11, minus 4, minus 2. And then plus 0, or minus 0, plus 0. So I take advantage, I go down the first column like this for my cofactor expansion. And then now that's pretty straightforward because this is just a 2 by 2. So it's taking 1 times minus 2, or 0 times minus 2, minus 4 times 11. So 0 plus 44. That is one way to get to the answer. There is another way we could have gotten to the answer, and that is to continue along our echelon form. So I'll rewrite that so it's clear. So this is a 1, this is a 0, that's a 0. So say I want to get this into echelon form. Well, I'm 1 step away. All I need to do is make row 2 swap places with row 3. Okay? But if I make those swap places, but the theorem tells me that that particular row operation, I need to make sure I throw on a negative. So I'm going to negate, so I need to throw on a negative sign. I have 1 minus 4, 2. But now by putting row 3 where row 2 was, and making those swap locations to get into echelon form, I did a row interchange. And for interchanges, I need to multiply that determinant, the new determinant, by minus, so that I don't change the value accidentally. Okay, so once I'm here, what did we learn at the end of 3.1? Well, the determinant of a triangular matrix is the product of its diagonal entries. So that's a diagonal entry, diagonal, diagonal. This is in fact echelon form, and so I have negative 1 times 11 times minus 44, which when you simplify that, of course, gives you 44. So those are two different ways, but two quick ways to get to a solution there. Obviously, this generalizes well for larger sizes of matrices. So be aware of that. It's a good example for computation practice, and then you're going to get a lot more computation practice in homework. Okay. I'm going to leave that up over there because that's kind of the most important part. So all that's really left to talk about is just a few points here. Suppose a square matrix A has been reduced to an echelon form, and we can call that echelon form capital U, by row replacements, and row interchanges, so swaps basically. And for a fun, something to know, we didn't really prove it, but it is true that if I have a matrix A, it is always possible by the row reduction algorithm to get an echelon form using only the row replacements and the row interchanges. You technically never need to scale. Then, so here's the result. This is going to generalize something that we kind of could intuit. The determinant of the matrix A is equal to minus 1 raised to the r power times the determinant of U. And since U is an echelon form, it is triangular. And the reason why we want it to be triangular is because then the determinant of U itself is just the product of its diagonal entries. Okay, so if I have some square matrix A, and I also reduce it to echelon form, and I call that echelon form U, then the way I can compute the determinant of A is to figure out how many row interchanges I've done. So the R here stands for how many times you have performed a row interchange. Not replacement, but interchange. That's where we were taking, like, row 1 and row 2 were completely switching spots, or like row 4 and row 6 are completely switching spots. That would add to the tally of your R here. And as we can see, what is this R doing? Well, every time you do an even number of swaps, you cancel out the negative that gets tacked on every single time. So each time you do a new R, you're tacking on a new negative sign on the front, and then that's just an easy way to think about it. An even number of these, positive. Negative number, negative. And then the notation here is determinant of echelon form is the product of entries U11, U22, etc. to UNN, where those are just the diagonal entries again. And if you're not entirely sure about this, again, just make sure you review 3.1 lecture, and that especially the very last example. Okay, so here's a theorem. We actually, funny enough, we covered this in 3.1 anyway, but I'll write it down because it technically comes up in this section. A square matrix A is invertible if and only if the determinant of the matrix is non-zero. Okay, we've already talked about the sum from earlier, but this is now officially general. We've generalized it to all square matrices A. And what's the key word here? Invertible. We're interested in invertibility, or the existence of an inverse, and so this will become a part of the ever-growing invertible matrix theorem. So that's kind of a key thing. This is a new part of the invertible matrix theorem, which you're going to continue to memorize throughout the class. Okay? So don't forget all the stuff you already memorized, because we're adding on to it now. Here's a simple theorem. One that, well, we may prove this one, maybe not. But it's good to know for convenience sake. If A is an n by n matrix, then the determinant of the transpose of A is the same thing as the determinant of A itself. Here's your multiplicative property. This is a huge one. You really want to know this. So the multiplicative property. This is going to come in handy for proofs. So it's kind of a big deal. And it's good that it's simple. If A and B are n by n matrices, then the determinant of the product AB, okay, so if I multiply A and B together, and now I want the determinant of the resulting product, that's the same thing as if I did the determinant of A separate and multiplied it by the determinant of B separate. Okay? Now, there is one trap, and it's the trap that you may think that you can do this with addition. You cannot. Here's the warning. So, warning. I'll put this in a big warning box, okay? The determinant of A plus B is not the same thing as determinant A plus determinant B, okay? You cannot do that. So do not be trying this. It's kind of, it's a similar mistake along the lines of like the classic algebra mistake in Algebra 1 in high school, where A plus B squared is not the same thing as A squared plus B squared. Okay, so that's not true, whereas the counterpart, AB squared, is actually, in fact, A squared times B squared. Okay, this is like high school algebra, so it's kind of, it gives a similar type of behavior. Don't think of it as actually analog, but just know, don't do this, okay? You're allowed to do this, do not do this. You're allowed to multiply them, but you are not allowed to separate them out if they've been added, okay? So it's the main thing. Things to really understand. Really memorize this theorem that's been hanging up here on the left side. Did some practice. You'll practice plenty with the homework, and then just be aware that if you have a hard time keeping track of the echelon thing, just keep a count of the number of times you swap. Because guess what? If you're able to get to an echelon form and you never swap out rows and it's all just replacements, fantastic. You don't need to worry about swapping the sign at all. You can just take that determinant down the diagonals and it's fine. Otherwise, you are just keeping track of how many times you need to swap out rows, and then it's the same exact thing. Just go down the diagonal of your echelon and it's all great. Okay. And then obviously, if one of those diagonal entries is 0, that means you have a free variable, and by invertible matrix theorem, no go, and so we're going to connect that here to the determinant of A, requiring it to not be 0 if we're going to have an inverse. And then lastly, know that if I take AB, I can split out those determinants in the product, but cannot do the same thing analogously with addition. Okay. So that's it for this short little mini section 3.2. Make sure you have this done before we hit Kramer's rule in 3.3.